We already discussed that processors execute programs. Programs are sequences of instructions, and each instruction is executed in a few steps. In this video, we'll explain the essential stages of instruction execution. You can find in the literature that there are 3, 4, or 5 stages of instruction execution. Everything depends on the level of detail one considers. The 3-stage description says that there are fetch, decode, and execute steps. The 4-stage model says that there are fetch, decode, data read, and execute steps. The 5-stage version adds another final step for writing the result back and sometimes reverses the steps of data read and execution. It is worth remembering that even a simple fetch step can be divided into a set of smaller actions which the processor must perform. In modern constructions of processors, every instruction execution can be split into a number of stages that varies from a dozen to even more than 30. The real execution of instructions depends on the processor's architecture, implementation, and complexity. Let us consider the 5-stage model first. In this model, we can describe 5 general stages of instruction execution. First, instruction fetch. The processor addresses the instruction by sending the content of the instruction pointer register on the address bus. The processor reads the code of the instruction from program memory through the data bus. The processor stores the code of the instruction in the instruction register. Processor prepares the instruction pointer, possibly it increments the instruction pointer to point to the next instruction in a stream. The second step, instruction decoding. A simple instruction can be interpreted directly by the instruction decoder logic. More complex instructions are processed in some steps by microcodes. Results are provided to the execution unit. The third step, data reading. This step is performed only if the instruction requires reading the data. The processor calculates the address of the data in the data memory. Next, the processor sends this address by address bus to the memory, and the processor reads the data from memory and stores it in the accumulator or general purpose register. Next step is instruction execution. The execution unit performs actions as encoded in the instruction with symbol or with microcode. In modern processors, there are more execution units and they can execute several instructions simultaneously. And the final stage, writing back the result. The processor writes the result of calculations into the register or memory. As we can see, during each of these stages, the processor performs a few smaller operations. In modern machines, each of these small operations is executed by a different internal unit, which allows the processor to work on them simultaneously. Such a hardware implementation of a queue of many instructions at different stages of execution is named a pipeline, and the processor containing it is named a pipelined processor. We will discuss it in the following video. From the perspective of a programming engineer, the program is a sequence of statements written in a chosen programming language. It is translated by an interpreter, compiler, or assembler software into instructions encoded in machine code. From the perspective of the processor, instructions are binary codes, unambiguously determining the activities that the processor is to perform. Instructions can be encoded using a fixed or variable number of bits. A fixed number of bits makes the construction of the instruction decoder simpler because the choice of some specific behavior or function of the execution is encoded with the bits which are always at the same position in the instruction. On the opposite side, if the designer plans to expand the instruction set with new instructions in the future, there must be some spare bits in the instruction word reserved for future use. It makes the code of the program larger than required. Fixed length of instructions are often implemented in RISC machines. For example, in the ARM architecture, instructions have 32 bits. In AVR, instructions are encoded using 16 bits. A variable number of bits makes the instruction decoder more complex. Based on the content of the first part of the instruction, usually a byte, it must be able to decide what is the length of the whole instruction. In such an approach, instructions can be as short as 1 byte or much longer. An example of a processor with variable instruction length is 8086 and all the further processors from the x86 and x64 families. Here, the instructions, including all possible constant arguments, can have even 15 bytes.